Let's practice some standing wave problems. Here we have a string fixed at both ends. We'll say the length is 50 centimeters. What's the simplest standing wave that we can draw? If you did the lab with the slinky, you should see that it's either going to go up or down. We're going to have a crest, and then a moment later, a trough. Each end is fixed, so we have to have a node at each end. This is half a wave. So what's the wavelength? Now, think about that before I go on. Well, if this distance is 50 centimeters, and that's only half a wave, then a full wave, it would have to be 100 centimeters. Now, let's say we measured the frequency at 2 hertz in a lab. What would be the velocity of the waves traveling along the slinky? You can use velocity equals frequency times wavelength and have 2 meters per second. The simplest mode of oscillation is known as the fundamental harmonic. What would be the next mode of oscillation? Pause the video, try to draw it before I do. Again, since both ends are fixed, we have to have a node at each end. The only way to have more waves and still have a node at each end would be to have one full wave. We've gone from half a wave to one full wave. So we can say this is 2 half waves. It's the second harmonic, labeled such because there are 2 of the fundamentals. What's the wavelength? Well, if this is one full wave, the wavelength must be 50 centimeters. Now, can you find the frequency based on the previous information? Using velocity equals frequency times wavelength, and we know that the velocity hasn't changed. It's the same string, but the frequency is going to change because the wavelength has changed. Plugging in the values, we get 4 hertz. That makes sense. The wavelength was cut in half, so the frequency had to double. What's the next mode of oscillation? And once again, pause the video and try to draw it first. We're going to squeeze in another half wave. It has to go up by multiples of half waves. So yeah, we have the fixed ends, the nodes that are at the end. We have 3 half waves. That's 3 of the fundamentals. So this is the third harmonic. Now, can you calculate the wavelength? Pause the video, try it first. Can you figure it out by looking at the picture? There's 3 half waves. This distance is 50 centimeters. How long is one of these half waves? Each one is 16.6 repeating centimeters, but we need 2 of them to get the wavelength. So it's 33 1/3 centimeters. Now, can you figure the frequency? Pause the video. That velocity is still the same velocity as we have up here. But what's happened to the wavelength? It was 100, now it's 1/3 of that. That means the frequency has to triple to become 6 hertz. Now, this pattern will continue as we go higher and higher on the harmonics. There's a 4th harmonic, a 5th harmonic, etc. Each time we go up, we add a half a wave. There's nodes on each end. Now let's say we allow one end to be free. The other end will remain fixed. Not so easy to do with a slinky, but if we have a flexible rod, one end can stay fixed while the other end wiggles. So what is the fundamental mode of oscillation, or the simplest standing wave we can form? There must be a node on this end, and if this end is free, there can't be a node there. If it can wiggle, it will. So we have only 1/4 of a wave, and it's the fundamental. All right, what's the wavelength? Pause the video, figure it out. If this is 50 centimeters and it's only 1/4 of a wave, then a full wave would have to be 200 centimeters. Now let's say we do a lab with this flexible rod and we measure 4 hertz. What's the velocity? We can use velocity equals frequency times wavelength and calculate 8 meters per second. What's the next mode of oscillation? Pause it, draw it first. Well, you're going to have a node on this end, and the other end has to be free. And the only way to add in more of a wave and still have this occur where that end is free and that end is fixed is to have 3/4 of a wave. So if a quarter is the fundamental, this must be the third harmonic because there's 3 of the fundamentals in this pattern. So figure out what the wavelength is. Look at it this way. You've got 3/4 waves. Take this distance and divide by 3 to calculate this length. If you know the distance of 1/4 of a wave, you multiply that by 4 to get the full wavelength. We get 66.6 repeating centimeters. How about the frequency? The velocity is staying the same. We can calculate the frequency. We get 12 hertz. Now you might look at it this way. The wavelength is cut to 1/3. So the frequency must triple. Let's take a look at the next harmonic. Pause the video, try to draw it first. That is one more half wave than the previous pattern. So what are we up to? It's 1 1/4 waves or 5/4 waves. That's 5 of the fundamentals. So we call this the 5th harmonic. Now use the same logic as we did here to calculate the wavelength. There's 5 quarters, so take 50 centimeters, divide by 5, and you're going to get 10 centimeters. Multiply that by 4, and you get the full wavelength. Look what's happened to the wavelength. So the frequency is going to have to be 5 times the original. Again, this pattern also continues on, always adding half a wave. So we have the fundamental, the 3rd harmonic, the 5th harmonic, and then the 7th harmonic, and so on. And now what if we have a system where both ends are free? Now that's really hard to picture. It certainly can't be a slinky. Well, how about the wave machine at school? It's a metal rod with a bunch of cross pieces and small masses at the end, and this can oscillate up and down, sending waves back and forth. It's really a torsional wave is what this is called, but it's supported on each end, so you don't have to worry about this thing collapsing. The rods at each end are free to move up and down as the wave bounces back and forth. Now you can make one of these things at home. Instead of a metal rod down the middle, use duct tape, and then lay across the duct tape some shish kebab stickers and put gummy bears on the ends. You'll have yourself your own wave machine at home. So what's the simplest standing wave that you can form here? Has to be free at both ends. So the fundamental is half a wave. That's 1/4 and 1/4. What's the wavelength? Figure it out. Has to be 100 centimeters. Now again, we'll do an experiment with this wave machine and we'll measure the frequency. Let's just say it's 3 hertz. What's the velocity? 3 meters per second. So what's the next mode of oscillation? What if I started shaking this thing a little faster? What pattern could appear? It's got to be free on both ends. So that means we have to have a maximum on each end, and we squeeze in another half wave. We have 2 of the fundamentals here. That makes a full wave. This is the 2nd harmonic. What's the wavelength? It's a full wave, so it's got to be 50 centimeters. What's the frequency? Well, we've cut the wavelength in half. The velocity stayed the same, and we get 6 hertz. What's the next mode of oscillation? You got to squeeze in another half wave. It's 3 half waves, making this the 3rd harmonic. Just to make sure, we're going to start here and go to here, which is half of a wave. Going up to here is another half of a wave, and then to here is yet the last half wave. So we have 1, 2, 3 half waves. Calculating the wavelength. 1/2 of the wave is going to be 16.6 repeating centimeters. It's 1/3 of the length. So the wavelength must be twice that at 33 1/3 centimeters. We've cut the wavelength to 1/3, so we're going to triple the frequency. And remember, the velocity is based on the median. That hasn't changed. It's the same velocity all the way down. Now you can see all three of these examples at home. The first, fixed at both ends with the slinky. You can do one end fixed and one end free with the beads. Have the beads dangle, and then you can swirl them around, and that would be circular standing waves. And if you want to, you can make yourself a torsional wave machine with duct tape and the skewers and some gummy bears. Of course, all of these have been seen on video as well, besides doing them in lab.